Now, before I show you the new recurrent architectures that we're going to continue on with, I want to give you a different view of recurrent neural network models in general, which is a very popular visualization, originally due to Christopher Olah. You're likely to see it elsewhere in the literature or in popular writings, and so it's very useful to get familiar with it. And just to familiarize you with the way to read this, these lines denote the passage of information. When the two things join, you can think of it as a concatenation. And then before you hit anything like this is a nonlinear activation function. But before you go through a nonlinear activation function, you update by multiplying through with a weight matrix, that is making a linear transformation. And so just to recapitulate, the SRN update rule on this view, you can read off of this as H sub t. That's going to be this new thing, which you'll see here and also is passed on into the future, is going to be a nonlinear update, in particular the tan H operator, of some nonlinear transformation of the preceding input state, H sub t minus 1, together with a nonlinear transformation, a linear transformation in both cases, of the current input X sub t. So that's the SRN architecture, but we can swap out the SRN unit. So you can think of this thing as a unit, and I could say, well, maybe I don't want this thing anymore, and I want instead to have some other kind of different architecture that maybe has features that are more suitable to language. And that's what we're doing in the next two candidate architectures. So the first of the two architectures that we're going to look at is what's called the gated recurrent unit. This is a more complicated looking unit, but I'll step you through it. There are 4 equations that characterize it. So the first thing that happens in this unit is that, as before with the simple recurrent network, the preceding hidden state and the current input are concatenated together. But before we get to actually a hidden state update, what happens first is that there's a nonlinear transform. Well, there's a linear transformation followed by a nonlinear activation that comes and gives us something called R. R is one of the two gates in this model. And what a gate is it's something that controls access to some kind of information. In particular, the way that R works is understood when you look at the next equation, which is the combination of R together with the preceding hidden state. Okay, and this X thing is what's called element-wise multiplication. It's this thing right here, and element-wise multiplication is illustrated down at the bottom of the slide. So the element-wise multiplication of two vectors is pretty straightforward. So for example, 1, 2, 3, element-wise multiplied by 1/2, 2, and 1 becomes 1 times 1/2 is 1/2, 2 times 2 is 4, and 3 times 1 is 3. Okay, so very straightforward element-wise multiplication. Okay. Now, what this update rule says is that you can think of H tilde as a candidate new hidden state. Okay, and that candidate new hidden state is computed in much the same way as the traditional SRN, except that the R gate controls access to the previous hidden state. So to the extent that elements of R are small, parts of the hidden state are going to be forgotten. To the extent that elements of R are large, those parts of the hidden state will be remembered and carried through. And then you wind up with this candidate new hidden state. But that is not immediately adopted as the new hidden state. Rather, instead, another gate is then computed. This is the Z gate. And the Z gate comes from, once again, the concatenation of the preceding hidden state and the input. Based on those two things, together with a nonlinear activation function, we get Z. And Z controls the extent to which we're going to carry through the previous hidden state unperturbed versus update the hidden state to reflect the candidate. Okay, so once again, so what we see here is that elements of Z should range between 0 and 1. And when elements of Z are large, you're going to have a very small update from this first part right here. So to the extent that elements of Z are large, this part is not going to contribute very much to the new hidden state, and the candidate hidden state will contribute a lot. But to the extent that elements of Z are small, the candidate hidden state is not going to contribute very much, and rather the previous hidden state is going to just continue on unperturbed. So at a conceptual level, what the GRU architecture allows you to do is it gives you a mechanism for carrying forward information in the hidden state over a period of time unperturbed, because of this ability of the Z gate to not pay attention to the candidate updates. Okay, so that's the fundamental insight of the GRU architecture. And that's one of the two architectures that we're going to look at. The other architecture is what's called the long short-term memory, or LSTM architecture. This is actually an older architecture than the GRU architecture, but it's a little more complicated. And the origin of the GRU architecture was the idea that the LSTM is benefits from gating, but the idea was that the GRU architecture is a simpler architecture with hopefully the benefit of gates. We'll see that at the end of the day what the relative strengths and performance of the models are. Okay, so inside the LSTM unit. So recall that as in all cases, the hidden layer h sub t-1 was used to predict element t of the sequence, the input that was going to happen at time t. Okay, now with the LSTM unit, the state representation is divided into two parts. There's the hidden state h, but there's also the cell state c, which you can see in the in gray here. We're going to look at that in a moment, but I'm going to start by showing you what happens with the hidden state. So first of all, as before, the hidden state and the from the previous time step and the current input combined together. They're multiplied through by a weight matrix and passed through a nonlinear activation function. But that creates, the first thing that does is it creates a gate. That is the forget gate, okay? This is the forget gate F. And what F is going to do is, we'll see this on the next slide. But first, we're going to look at the next thing that happens, because there's another gate that, that gets created. The hidden layer from the previous time step and the current input are then, first of all, they're passed through a nonlinearity, this creates an I, or an input gate. And the input gate is going to then update that cell state, which we're going to understand a little bit better in a moment. First of all, a candidate cell state C tilde sub t is generated. This looks very much like a traditional SRN update rule. This is, once again, the weight matrices applied to the preceding hidden state and current input respectively, and we get a candidate cell state. Okay, and now these two things are combined in the following way. So here's the next step, which is that the cell state, which you can think of as a sort of longer term store of information that can be taken and used, remembered, forgotten, but it's relatively easy in this architecture to remember over a long period of time. This candidate cell state is updated in a way that looks a lot like the GRU's hidden state update rule. So the forget gate and the input gate will control the relative contribution of how much the preceding cell state is just passed along unperturbed, and how much the cell state is changed by adding new information to it. Okay, so the forget gate tells me, once again, this is element-wise multiplication here. So the forget gate, to the extent that the F values are large, we're going to remember the preceding cell state. And to the extent that the F values are small, we're going to forget the cell state. Remember, the forget gate is created by the hidden state and the current input together. So those two together are going to tell me what I want to do with the preceding cell state information. But then also, to the extent that the input gate values are large, the I's, I'm going to now add new information from this candidate cell state update into the cell state. To the extent that the input gate values are small, I'm just going to ignore that candidate update rule. Okay, so that's the perturbation of the cell state. And whatever happens as a result of this, this is going to get passed on to the next time step. So actually, the cell state really can be unperturbed for quite a while, actually, in this representation, and it can be modulated and changed in a relatively straightforward and understandable way in principle. We'll see this a little bit more going forward. Finally, we have to ask, well, what does the model actually do to the hidden state, which is important both in predicting what the next word is going to be and in modulating how the new input is going to be treated. And this now, we're going to create another gate, which is the output gate, which tells me that, so fundamentally, the hidden state for that we have, which is the new hidden state, is going to be some function of the cell state. It's going to be some readout of the cell state, but the nature of the readout is going to be controlled by another gate, the output gate, which once again comes from the preceding hidden state and the input nonlinear activation function, and that's the output gate. And we now simply apply a nonlinear activation function to the cell state, and then we gate it with the output gate, and that's our new hidden state representation. So to summarize, this is the complete LSTM unit. It has this set of equations. It's more complicated than either the SRN or the GRU, but it actually is a very powerful architecture. We're going to see in a moment a simple example of its success in studying language.